that expansion and contraction changes the angle.
I see. Since I wasn't going before, Greg nicely pointed out, we're looking at laser design. Tunable frequency laser design. I get it now because we're tuning it by changing this grading. Got it. Okay. Okay, laser stability. To promote laser stability, we control temperature to within 10, what's a MK? Millikelvin. Okay. Insulate from vibrations, properly collimate.
So you can think of collimate as becoming like a column.
A column.
Collimation is taking this cone-like, it's like a cone when it comes out of the laser diode, and it's making it a column. So it's straight. If it wasn't, then you would have different angles hitting the grating and different frequencies going back to the diode.
And how?
And that creates extreme instability.
I see. So you need to focus it.
How do
It's
they
basically
make it?
focusing.
How do they make it do that?
By adjusting the distance that the lens is away from the diode.
So the
that's
lens is
interesting.
just like curved in like a way
Yes.
that it's focused.
So the stuff is coming out of the diode, or is it going into the diode?
It's
The light.
going out and coming back in. The reason it needs to go back in is in order for it to laze, it has to have that feedback.
I see. Laze is a verb that means what?
To act like a laser.
Act like a laser. Okay. So we're doing this to laser stability. Laser feed forward. Laser is unstable if only grading angle is changed.
So if you only change the grading angle, it will look like this. This is changing frequency, and this is grading angle.
I see. So this is the grading angle.
Yes.
I see. And by tuning this knob, we can get these different effects.
Yes.
The change in frequency.
Well, actually, so we by applying feed forward, we can make it look like this by applying current to the laser diode proportionally to the grading angle change, and we can make it nice and smooth.
And that's important?
Because we want to have nice, smooth frequency change. We don't want to be jumping all over.
I see.
We want to be able to control it very nicely. We
I
just
see.
want to say, go to this angle and then have it be at this frequency.
I see. Okay, laser is able to tune to arbitrary wavelengths between so and so with fully continuous tuning around these wavelengths of at least blah to blah. Okay. PLE setup. So this is the sort of design, and this is what you get here.
Yeah.
This whole bunch of junk here.
Yeah.
How does this and this help you build a computer?
Did I mention that the zero photon lines of two NV filters have to be identical to create entanglement?
I don't.
No
Okay,
entanglement.
I must
By
have
entangling more NV centers, quantum computations can be done.
Yeah, but-
So we're interested in entangling these things.
Yes, so this is a method to look at the zero photon line representers very accurately. And we need to do that because we need to make sure that they're identical. And we can change the zero photon line by Stark tuning, and that will stabilize.
That means
and
applying
make it
electricity.
identical.
Start tuning.
Yeah, basically.
Okay. Okay,
But
good.
when that happens, then that means that something.
So we have a laser, then we have an isolator, and we have a BS.
Beam splitter.
A who?
Beam splitter.
A beam splitter, and that goes to the NV, which is the nitrogen
It
vacancy
basically splits
center.
light into all of the different things that we need it to do.
Okay, so this one beam splitter puts out this, and some of the light goes through further,
Yes.
and then it splits. This one splits it to this, and this one splits it to this.
Basically.
Then a power
It is-
meter.
I didn't actually set it up like that. See how it goes? The prisms are beam splitters.
I see.
And it goes like that, actually.
I see. The laser scans over the range of frequency. Meanwhile, frequency and NV-PL intensity is recorded. These are graphed as our spectrum. Notice no misspelled words so far, Greg. Determined. So this is
We have spell check.
determined laser frequency X. So what are the variables on the axes?
Laser frequency, and I should have labeled these axes.
Yeah, Y and X. Okay, and determine
intensity.
normalized PL intensity. Oh, it's the normalized PL intensity.
So because we're changing the current, the intensity of the laser isn't the same over time.
I see.
So we need to normalize it by dividing by the power in this that is detected by this power meter.
I
So
see.
we normalize the photoluminescence for you.
Okay. Future PLE results. Example PLE spectra at Y, Z over time X. No Stark tuning stabilization. Oh, with Stark tuning stabilization.
See?
That's the whole
Smooth
purpose
and
of getting this to work out. I see.
Also to make the zero phonal lines identical.
The what's identical?
The zero phonal lines identical. of 200
Zero
seconds.
phonon lines as a ZPLs.
Yeah.
Zero phonon line. I see. And when we have these things more stable, then we can more readily apply this to practical computing.
Then we can actually entangle them.
Then we can actually what?
Entangle them.
Entangle them.
Because it's
And that
only-
enables us to do it to computing.
Yeah.
I see. Yeah, but because it's easier to entangle two,
Two stable things instead of something that's going all over.
yeah. And the whole purpose of this is to get this a smooth line, kind of.
Yeah.
One of the purposes. Okay. Very cool. Let me go take a quick view outside before they all start closing down. Just 1 second. I'll be right back. I'll be right back. Okay, here we have more people. We have more people. And let me see if I can see downstairs here. Let me just take a picture. There's more people in the typical poster sessions. This is in Mary Gates Hall.